Well, hi everyone, let's get started. It's my pleasure to introduce Bert Zwart. Bert, thanks for coming with you. I think this is your second time visiting us. That's fantastic. So today, Bert will give us a talk on how to avoid blackouts at minimal costs using chance constraint programming. That's a perfect topic at the interface of applied mathematics, probability theory, and energy applications. So I'm so eager to hear your talk. But before you starting, I would like to introduce you, Bert. So Bert received his master's degree in econometrics from VU Amsterdam in 1997 and PhD degree in mathematics from TU Eindhoven in 2001. He's the leader of the CWI stochastics group in Amsterdam and professor at TU Eindhoven in Netherlands. His research interests include applied probability and stochastic networks. Bert's work on power systems focuses on applying probabilistic methods to scheduling and reliability issues and rare events, such as cascading failures and blackouts. He has been a stochastic models area editor for operations research. That's the most prestigious journal at Informs for OR. From 2009 to 2017, and currently serves as editorial board of 5 journals. Bert was co-organizer of a special semester on the mathematics of energy systems taking place in Cambridge in 2019. So Bert, the stage is yours. I suggest that if we have a small questions, maybe we can interrupt you, Bert.
Yeah.
But if you have a big, longer philosophic question, maybe we can leave it to the if
there's something not clear on the slide, do interrupt me.
Well, Bert,
thanks a lot to everybody for having me here again. I was here in March 23, and it was a very inspirational visit. I met many people, and one of the things I realized is that people here at DTU like chance constraint. That's the thing they like among many other things, and that was kind of inspirational in a way. And so today. I put my own twist to it as a mathematician. So today I'm going to talk about joint work with José Blanchett from Stanford, Joost Jorritsma, who did a postdoc at CWI and now is at Oxford in the math department. And the title of this talk, it's more like a wish, a desire, an ambition than that we have solved this problem, of course. I will make the connection between chance constraint programming and blackouts. So let me begin a little bit with blackouts. So blackouts obviously are disruptive, but like one can expect that the nature of blackouts may change when we shift more and more towards renewables, because if we have to handle renewables, we have to manage the system in different ways, and that can create other problems in blackouts. And so as a mathematician, like blackouts are kind of like a magical thing, especially if you're working on extreme value theory and rare events. In the Netherlands, we have been having other problems like a flood in 1953, and we developed extreme value theory to kind of manage the dikes of the heights in the 80s, and in 2008 we had problems in financial networks, and we had to we had to decide how much buffer capital banks need to keep, and in a way the power grid is next on a certain abstract level. Of course, every different application comes with unique challenges, and so here are, this is a slide from DNVGL. These are like a couple of blackouts up to 2015. It's an old slide. It's a very nice slide. So yellow is Asia Pacific, green is Europe, and then the bigger the circle, the bigger the blackout. And there is a duration versus when they occurred. And so all of these blackouts have a unique story that if you would write this as a script in a movie, the script would be rejected because it's too unrealistic. So like usually there is a chain of ridiculous events, combination of ridiculous events that precedes a certain blackout. And so it's kind of questionable. You could ask yourself the question, what can we do with mathematics here? What can we do with modeling? What are you going to include in the model? So here is all the data on successful squirrel attacks to like squirrels, or birds, or snakes, martyrs, like anything can lead to system failure. And so like the bottom line is that as a mathematician, usually you can put two things in a model, maybe three, and then quickly it gets out of control. So we have to be thinking about how to deal with that. But there are certain things. So there's actually EU regulations. I'm not a big fan of reading regulations, but Jalal found this one, more or less. And Article 153, item 2C on FCR dimensioning. And so you don't have to read this. So the bottom line is that it is possible the TSOs are allowed to develop a probabilistic dimensioning approach for frequency containment reserves in such a way that the frequency stays within acceptable levels almost all the time, with the exception of once every 20 years. There was a call for consultations last year on how that should be established. They suggest to run a Monte Carlo simulation for 200 years for a fixed set of reserves, and then run your simulation for 200 years. If there are more than 10 system failures, your reserves are not acceptable. It's a very interesting discussion on whether that's the right way to do it, but I'm not going to talk about that today. But the bottom line is like this: once every 20 years. And so you could think about the frequency almost all the time should stay between 49.5 and 50.5, except once every 20 years. It's allowed to go below. And so that would lead to a chance constraint. And so what we're doing here, so this is first of all, point is that you get a probabilistic constraint. And second of all, we replace blackout with some, blackout is kind of like a second order reliability problem. We replace it with a first order reliability problem. Now the idea is, you can also think about voltages, but the idea is that if we make sure that the frequency stays stable, then we don't expect the blackout to occur as long as the frequency stays stable. So it kind of makes sense that I don't think that, like usually with these blackouts, the frequency at some point got out of control. So like frequency is a first order problem, and it's more measurable than saying we need to prevent so many households having no power for so long, so many hours. It's very, very difficult to put that into a model because a cascading failure sequence is very, very unpredictable. And so this is kind of more manageable that that's the idea of this. And then you can use maybe chance constraints. So that's kind of like a little background, and now delving into some math. So here is a basic formulation that at least we considered in our work with Jose and Joost. We were maximizing a linear profit function subject to some deterministic constraint. X is in some set capital X. We're going to ignore this, and we're going to focus on a chance constraint where the probability that phi of x and L exceeding 1 should be small. So phi is a function that basically, for example, in a power grid application could be deviation from 50 in the frequency, and 1, the critical level that you should not allow to exceed is set at 1, just to normalize things. It would be a half in frequency application. Right? And this is the deviation from 50, and this is a half. And then L is a random vector. It contains randomness. Can have all sorts of elements can be random, like supply and demand of electricity, for example, or like just failures of assets would also be encoded there. I will assume that phi is convex in X, and this delta is the risk tolerance. And I'm going to assume in my analysis, at least, like I'm going to show later a few mathematical results, and I'm going to be interested in the case where delta is small. So this type of setup has not just applications, that has applications in many fields. Like, as I said, my motivation, inspiration comes from power grid, but you can also think about financial planning, communication network design, and also the design of bridges in aircraft. So like, for example, in aircraft, an aircraft is designed in such a way that the probability of failure is 1 in a billion per hour of flight. That's kind of like an example. And so a very good question is like, well, if you have such a small probability, why don't you just set it equal to 0? After all, the difference between 10 to the power minus 4 and 0 is just 10 to the power minus 4. But of course, the difference here are not absolute but relative. So they're like There is an illustrated numerical example in an early paper of Shapiro and Nemirovsky, where they show they solve a chance constraint problem for delta 10 to the power minus 12, and then they solve it for 0. And they show that the difference in costs, the relative difference, is like a half. And often setting delta is equal to 0 is actually impossible. That the only solution would be to do nothing, to just be absolutely safe. So it's kind of like it's good to think about this region, like setting it equal to 0 may not be the best idea. So I'm not maybe talking about this next time I'm here, hopefully soon, but like let's first enjoy this visit. So we have ongoing work on a power grid application with Jupke Janssen and Jalal and Alessandro from the VU. And we are there, we're interested in this FCR problem I was mentioning earlier. And if you look at these markets, the goal of this FCR markets is to procure enough reserves for an hour. If you translate then the probability of not procuring sufficiently many reserves in the next hour, and you renormalize this once every 20 years to hours, you get a small number. I hope I did the computation correctly. So here, it's like it doesn't really fit into this framework. To be honest, I use this for mathematical convenience to just understand certain things first better. Here, you have a dynamic problem. The frequency is a dynamic process. You assume the frequency is okay at time 0, and it needs to stay with high probability inside a safe region with a high probability. You get like more like exit problems, like so you have a dynamic problem, while here I formulate it as a static problem. I'll give some references later to a power grid application. But like L and phi, I'm taking them relatively stylized scale. So still, then there are challenges. I'm just listing 3. I'll mention 2 more at the end of my talk. First of all, if you're familiar with chance constraint problem, you know this, but it's important to mention, even if this function phi is convex in X for every realization of L, then the resulting set of feasible X such that this chance constraint is satisfied may not be convex. So that's a problem in optimization. If things are not convex, a local optimal may not be a global optimal, as you know. And so that's a problem. Then you have to, already for a fixed decision X, you have to compute this probability from a purely computational perspective. That can be a very hard problem. And then there are other problems that appear if delta is small. Like, for example, if you want to approximate this probability by simulation, by Monte Carlo simulation, if delta is small, if you want a reliable estimate, you need many samples. So there are like 3 different formulations of the original problem that try to mitigate certain aspects of this. First of all, there is the CVAR restriction. I will go through them in a minute. Then there is a sampling method, and then I want to bring your attention to a third method that is not new but less known, which is a bi-level rare event approximation. And the goal of this talk is to understand what are the merits of these methods if delta is small. So I'm not going to take any position of you should use this method. I'm not trying to sell a method here. I'm just trying to understand how these methods work. And sometimes one method may work better over the other and vice versa. It really will depend in practice on what your function phi will be. All right, so let's review these 3 methods over the next 3 slides. First method is the CVAR formulation. As far as it's a famous paper from Nemirovsky and Shapiro. There has been a Dutch operations researcher, Klein Haneveld, who suggested a version of that already back in the 80s. But I think Nemirovsky and Shapiro, they really showed, they pushed the analysis at least much further. I don't want to make any historical inaccurate comments. But this is a very nicely written paper, and has actually way more ideas than just CVAR. CVAR is section 2. Section 3 has other ideas. I don't even know section 4. I never got that far. So define CVAR like that. And so you have this, instead of a probability, you have expected value here. So the problem with probability is that a probability is an indicator function of an expected value. An indicator function is a discontinuous function. This is why the non-convexity appears. And here, essentially, you're replacing a discontinuous function with a continuous function, and that helps. And if you define C bar like that, and you add this constraint to your problem, instead of the probabilistic constraint, you get a convex program. And a feasible region of C bar delta is a subset of the feasible region of of the original chance constraint problem. And so you are safe here. You get a safe solution, and you have a convex problem. Now, of course, evaluating this still may be a computational challenge depending on phi. But still, at least you have a convex problem. That's the idea. So now the question is, how conservative is this going to be if delta is small? I'll get into this later. Yeah, so in general, this is conservative. How conservative? Like I want to know if delta is small, what to do there. Second main formulation that most of you probably know is a scenario formulation. Like I'm not a real expert on this, but this seems to be one of the first papers. You just simply sample k samples of L, and instead of solving this probabilistic constraint, you just replace it with a requirement that your decision X should satisfy this inequality for all k samples. And what is really nice is that what Calafiori-Campi shows that if you choose the number of samples k like this, then your solution is feasible with probability at least 1 minus beta. And the nice thing about that is that it is true regardless of the distribution of L and regardless of the function phi. This is really why it's such a powerful result. You can always apply it. Caveat is that this choice, if delta is small, then k is going to blow up. There are, however, papers of one of Shapiro and Nemirovsky, and I also worked on that in another work with Jose, where depending on if you make more assumptions on L and on phi, you can do a biased sampling, and then this level k can be made smaller sometimes. But like in the plain vanilla version, you need to choose k like this. And of course, like choosing k bigger and bigger has two caveats. Like the size of your problem computationally gets bigger if k is bigger, and also like if I choose a bigger k, the profit will go down. Right? There's like there is a tension between how many scenarios you include and what is the value of your optimal solution. Okay, the third one, which is not as well known, and I'll try to explain it to you, is like a rare event bi-level approximation. So the idea is hopefully simple. I'll try to explain it.
Can I ask a question?
Yes.
On the previous slide?
About the previous slide?
Yes. There is a way to trade off constraint. Have you investigated the fact that the scenario approach, you put okay, if I have a large number of samples, then might be too conservative. That's what you hinted. But I can also remove some of the constraints and sort of have a bound that depends. Was that something that you explore or that you've seen in the literature? It's also the scenario.
Yeah, I'm aware of that. People are trying to do that. Yes, but
how good they are in trading? I mean, I just wanted to hear your thoughts on if you thought about this way of removing some of the constraints.
Yeah, I thought about it.
And how good these approximation are in trading performance with delta, if you thought about it.
Well, I think it's better to discuss this afterwards.
Okay.
It's like I'm going to show good things about this anyway.
Okay.
Okay. So I'm not taking position of whether it's a good or a bad method.
No,
But this is like this is not a minor question. It's a big question. I can talk for half an hour about this.
Yeah.
Okay. So let's go to the third one. Okay. So the probability of failing our security goal can be written as an integral. Let's assume, for just the sake of explaining the idea, that L has a density. So we have to integrate it over a set G of X. With like this is all the realizations of L such that our security goal is not satisfied. And any idea is very simple. This integral, we replace it with an optimization problem over set G of X. And then using like tradition from statistical physics, if you want, we write this as the exponent of minus the infimum of the logarithm of the density. And now, if if this probability is required small, then typically L, the absolute value of L is going to be very big. The absolute value of the vector L is going to be very big. And then this density typically will scale, and you will get some connection with information theory. That's kind of roughly the idea. And the optimizing U is the most likely way to cause the event G of X. So for example, like one way of speeding up simulations and reducing the number of constraints is that you have a good guess of what the optimal solution might be. There's a paper of Asymptotic and others that they try to do that, to kind of guide somehow simulations. But even if you do this, you get you maximize profit such that not the probability is greater than or equal to 1, but less than or equal to delta, but such that this is less than or equal to delta. And then you get a bi-level optimization problem. And so there are a few papers that suggest that. And so there is one paper that I really like from Anirudh Subramanian and others. It only has 2 citations. I think it deserves more. I will cite it a few times. Anyhow, it's a very nice paper, but it's not for the faint-hearted. There's a lot of mathematics, and they do a lot of computational work, and it's like amazing what they did. I think I'm a big fan of this paper. Anirudh is not paying me. By the way, I say this voluntarily. And so what they look is like they look at the version of ACLPF, but not full AC, but also not DC. So lossless ACLPF. Like us, we just say, okay, blackouts are too difficult, cascades are too difficult, so let's just assume we want to limit the probability of a system escaping a safe operating region, and then they use this. They use the large deviation theory together with some very nice refinements, and they formulate a bi-level program, and then they managed to solve that bi-level problem within seconds for a 118 bus system. And they do all kinds of validation. Caveat here, I would say, is that they assume noise to be Gaussian, and that usually helps in this type of work. Okay. So what is the goal? I want to go beyond the Gaussian talk, and I just want to go beyond the Gaussian assumption. Assume as little things as possible about noise, allowing for dependence between the coordinates. And I want to understand for the original problem, if delta goes to 0, we know the smaller delta, the less profit we make. I want to know how this optimal profit scales as delta goes to 0. Qualitative result. Then, if you know how that scales, you can use this as a benchmark. Which algorithm achieves this optimal profit if delta becomes small? That was our goal for these 3 alternative methods. And we want to look also at the heavy tail case, not just Gaussian or exponential. We have to make another assumption. We're going to assume this bilinear form, that phi is the supremum of these bilinear functions. Okay, to develop intuition, so I gave this talk last week in Luxembourg, and I had to rush because people had to catch planes and all. And I thought, okay, it would be good to kind of, this is kind of still pretty complicated, but like the ideas in essence come from this example. It's the simple possible example. There is no computational challenge here. I take my risk level as x times L, and x and L are both one-dimensional. In that case, we can solve our chance constraint problem analytically, and we can understand how these other methods work in this case. So the explicit solution is just in terms of a quantile. So f bar is the tail of L, tail function of L, and we take the inverse at the point 1 over delta. And that's the optimal solution x. And so if we take L to be exponential with rate lambda, then the optimal solution would look like that. Then we can compute this inverse analytically, and in the case of the Pareto distribution, the optimal solution will look like this. So we can use this to get some intuition on how the other methods will work. So let's assume first that it's exponential. So just to repeat, the optimal solution is this. If we do this bi-level thing here, if we do this, so we have the density of the exponential and so on, and we compute everything. I'm not going to bother you with the computations, but we get something that looks the same as here, but there is in the denominator an extra log lambda. If we do it for the CVAR, again, we'll not bother you with computation, we get an extra delta here. So you see that the X under CVAR is always smaller than the optimal value. However, if delta is small, it's actually pretty good. It's just a little delta here. Like if delta is small, 1 over delta is large, so the log is large, so this whole thing is small. But like if I divide the CVAR by the optimal value, the ratio goes to 1. So it will be of the same order of magnitude. High-level approximation, the very event one, actually, it may not be feasible if this, it depends on the sign of log lambda. Whatever I'll say the wrong thing, but it's only correct if log lambda is equal to 0. So if lambda is bigger than 1, it's not feasible, or if it's less than 1, like either way. But you have to be careful. I did the computation while preparing the talk. If it's less than 1, bi-level approximation is not feasible. You have to be careful there if you really want to have a feasible solution. What happens in the sampling approximation? So in the sampling approximation is a fundamentally different thing because we use samples. And so once we have case scenarios, then we divide. So the optimal solution in this trivial case is explicit. You just take the maximum. And this is exactly what you said. They are redundant scenarios, right? This is exactly what you said earlier. You can lower the computational complexity by removing redundant scenarios. In this case, it's obvious what you have to do. You just take the biggest one, and that's easy. And in higher dimensions, you will always have certain planes that are irrelevant. There are ways to reduce it. I agree. So, but still, what you see here is that that's a computational complexity issue. Like you have to sample a number of scenarios and then removing the ones that are redundant to solve it computationally fast. But still, from a probabilistic point of view, if you have too many samples, then you should worry about optimality. But the good news here is that still under the Calafiori-Campi rule, for example, if I want to be feasible with probability 1 minus delta, then I'm almost always feasible for delta small. Calafiori-Campi rule will give us this, and if I choose beta is equal to delta, then okay, I have a 1 over delta log 1 over delta here, but because I have a log there as well, you still get the same ratio. So in a light-tailed case, Calafiori-Campi, yeah, it also behaves well, at least for this one-dimensional case. So how does this example extend to a more general class of functions phi and L? The answer, it does. So Calafiori-Campi, you will still get optimality for the light-tailed case, and CVAR also. But I'm now going to see, okay, let's see how the slide goes. We have a slightly more general setup, and it's kind of like extreme value voodoo modeling. So we're gonna assume that our random vector L, the logarithm Q of X, satisfies certain assumptions. Namely, if R, just think of R as the magnitude of the absolute value of L, of the radius of L. If this Q at a large value R kind of scales like R to the power beta times the function little lambda x. And this is a good framework. It comes from extreme value theory, and it really allows you to model dependence between large values of L. And it's kind of important, for example, if you want to model dependence between failures, to get that right. And so this is a good flexible framework to do this. If L is Gaussian, then QR is just R squared, and lambda has the inverse covariance matrix. There are other ways of modeling this dependence. There are like special copulas that model this. There are like extreme value copulas. There are all kinds of, but this is a nice one, which is very explicit. If lambda is given by that, it's a parametric way of modeling dependence. If theta is equal to 1 in the tail, the rare events in the individual coordinates are independent, and if theta becomes bigger, then the rare events become more independent. And so this has been a big thing in the financial world. Some people claim that the crisis if 2008 occurred because they modeled the dependence like this, like as if it was Gaussian. And so in the 80s, they realized that the returns of stocks are not Gaussian, but they are heavy tailed. But then they said, okay, we don't like, okay, the one-dimensional returns are heavy tailed, but now we have to model dependence. So you just do an inverse transformation of the individual coordinates to make the marginals be Gaussian, and then they model dependence, and then they model the joint dependence Gaussian, and you can transform it back, and then that worked until 2008. But like, I'm not sure, like there is like a discussion on whether that was really the problem. There were many other problems, but this type of dependence kind of doesn't seem to work well, at least in finance. So if you do that, so there is like mathematical machinery that you can have to define. So I have to define, so there's going to be a bi-level problem, and so I of B is the infimum over X of this lambda, this dependence function, so that P of X is equal to 1. And once we have defined this, we can approximate our chance constraint. Namely, we don't look at X, but X has to be small because we have a rare chance constraint. So we're going to normalize. We look not at X, but we replace X with a Y divided by R. So then this probability Y over R bigger than 1, it's just because of our function of phi is this maximum bigger than R. And then we can use large deviation extreme value theory to approximate the negative of the logarithm probability by this, where you get this I appearing here. And that's the theorem. I'm not going to go into detail why it's occurred, but this is what you then get. And so you get then the minimum over all these, and I call this J. And what you then get is that if you get this chance constraint is approximated by this J of Y times R to the beta. So this is the overall magnitude of your decision vector, let's say. And if you now, but like this probability has to be smaller than delta. So it turns out that R has to be taken equal to this. And if you do that, this constraint reduces, if you use this approximation, the original chance constraint just reduces to the constraint that J of Y is greater than or equal to 1. So in the one-dimensional case, that this J of Y is explicit, it's simple, but in general, you have an optimization problem. So if you do that, so why is this important? Well, if we go back to our chance constraint problem, it turns out that if we define Y star to be a solution of the problem of maximizing CY subject to this constraint JY greater than or equal to 1, then there we have a theorem that says that the optimal value of our chance constraint is equal to CTY star divided by this, up to a smaller order term. So that it kind of this bi-level problem naturally appears if you look at the sequence of optimization problems in a limit as delta go to 0. We have a theorem that says like, well, this bi-level problem appears, the solution of this bi-level problem appears in the limit. But it only, as a mathematician, I should say, it only appears in the limit of that it has a descriptive value. So I'm not saying you should actually use this in practice. It has a descriptive value. It appears in the scaling of the optimal solution, the optimal value. So you could use this as a benchmark if you want. And so this is an important caveat. If you use this bi-level solution, there's no guarantee of being feasible. I showed that in the one-dimensional example. We have in the preprint, we have a more elaborate example in higher dimensions. Is that it could be really bad. Like I showed, like on the slide of the one-dimensional case, it was just this log of lambda or something. But in higher dimensions, it gets worse. So you have to be careful. So if you're afraid of that, you could always, and you want to use this, you can always say, okay, I'm multiplying this with a certain safety factor. And I shrink my solution from the bi-level problem with a factor 1 minus eta. But then you accept a certain optimality gap. Okay, but this is just, again, this is just for the plain vanilla version. So in CVAR, we know it's feasible, and we found, we confirm like what we showed in the one-dimensional case, it's still true. In our more general class of functions, 5 for higher dimensions, that CVAR, you have a feasible set of solutions, and you get same scaling as the scaling of the true optimum. So there's like a first order optimality result. Like if you, so the ratio, both of them go to 0 as delta goes to 0, but the ratio goes to 1. Like the difference there may be a second order thing that you can ignore it fine, but at least this has to be up to 1. And finally, also the sample approximation. So you can also show here that the sample approximation. So from a probabilistic point of view, if I have k random vectors L1 up to Lk, I have a random linear program. The criterion for the objective function is deterministic, but my set of feasible regions is a random convex set. But extreme value theory has been extended into this realm. There are like results of Balkema and Resnick where they show that these random sets, if you normalize them correctly, they converge to a deterministic set. They converge to the same deterministic set as we saw in the bilevel, the feasible region of the bilevel. So there's a nice, it works very nicely. And then if you choose Calafiore Campi like that, you also get, at least for the light tail, that it works well. So the main drawback is that you need many samples if delta is small. Like in particular cases, you can reduce the number of samples either by doing biased sampling, or by using arguments that some samples are redundant.
Sorry, you said you don't want to take a position saying this method is better than the other one or not. But what I'm hearing from you, correct me if I'm wrong, is that if the problem is not heavy tail, light tail, you'll see one approximation. That's what kind of.
Yeah, all of them are pretty decent. Yeah.
But but if delta goes very small, then sample base is not easy.
No, but there are okay. So they're like first of all, like our a priori worry was that the optimal cost will be high.
Yeah.
And it turns out to be not that bad.
Okay.
And then if you want to, for computational reasons, there are more sophisticated versions of this sampling. Either after the sampling, you remove samples, as has been said in the audience, or there are ways of doing bias sampling, sophisticated ways that you could just.
And I have a naive question, it might be super naive. Do we know in advance whether our problem is heavy tail or light tail?
That's a philosophical question. Yeah. I mean, there are like disagreements on whether something is heavy-tailed or not in practice. Yeah, and then typically, I mean, with the frequency is non-negative, and it's surely below 100. I'm just saying some ridiculous. So things are bounded, but like when is something bound? When is it unbounded? It's sometimes hard to say. But like, but in practice you need. So I'm just trying here to say, okay, like more a scientist point of view, not an engineering point of view, is like, okay, we have these methods. Some of them are used, some of them are used less often. Like, how do they behave in this regime? Assuming my probability model is known. That's a big assumption. We can talk about it at the end more.
Sure.
So conclusion, I would say all of them work well. If you use the vanilla version of sampling, you need many samples. Computing CVAR may not be easy. So the bilevel problem, the lower level problem involves this lambda, this dependence function. And so it can really depend on the application. You really have to be careful. So like in this paper of Anirudh, they managed to reformulate this bilevel problem quite effectively. And they were able to pull that off. I think in the future, maybe they're like, I haven't looked at hybrid algorithms where you use the bilevel approximation in some way to do a guided sampling, and then you do a few samples to get a better approximation of your optimal solution, and then do kind of iteration. This is something that Henry Lam has a preprint on arXiv, and other people have been working on that. That's ongoing research. So let's go to heavy tails to see how things are there. So heavy tails are everywhere. So following up on your last question, when I was a PhD student, I worked on, there were like AT&T and Bell Labs, they were able in the 90s, they were able to collect data, and they found out that file sizes are heavy tails. And like the classical queuing models, they predicted bad things to happen. But then the engineers, they were rightfully saying, well, in a communication network, we don't do first come, first serve. That's a stupid way of engineering a communication network. What we do, we have a big file, we chop it into little packets, and then I'm watching a video, Jalal is doing a Zoom call, Lesia is submitting an email. All of it is chopped into packets, and Lesia's email is just 5 packets, and Jalal is 1 million packets, mine is 1 billion packets, and Lesia's packets will get through before we're done watching our movie or doing our Zoom call. And this is how computer system works. So the TCP protocol has fixed, it works regardless of the assumptions of file sizes. So it is not controversial that file size is a heavy tail, but like the algorithms are immune to this feature. In finance, it's of course a different story. People found out the hard way that they're heavy tail just by getting bankrupt. And so everybody got bankrupt. Nassim Taleb didn't get bankrupt because he knew that it was heavy tailed. And so Nassim was right. Social networks is another example that also in grants, we have seen this. There is this one professor that gets half the money from our science foundation, and the rest of us has to do it with the other half. We all know who they are in our countries, and it's the same, like the rich get richer. And then in blackouts, the size of a blackout is also heavy-tailed. If you do that statistical test, it's pretty, in the US, they have a good data set, and it's pretty clear it's heavy-tailed. Anyhow. So examples, the main example of a heavy tail I'm speaking of is the Pareto distribution. And what are the key, and there's also log normal and Weibull. They sometimes also considered to be heavy-tailed. Weibull, if this parameter beta is less than 1, there are key properties, namely that the moment generating functions do not exist. Probability that the sum is large is just the probability that the maximum is large. And for us, the main one is that this conditional expectation, if x is bigger than t, the excess is going to diverge. For the exponential, there is the memoryless property. This expectation is just equal to the expected value of x. Well, in a heavy-tailed case, it will diverge. In the case of the Pareto, it will actually be of the order of t. And in CVAR, this conditional expectation will appear, so it's important for CVAR. So, free book online, just a little commercial. If you want to read about, if you want to know more about heavy-tailed speed. JK is at an E department in Bombay. Adam is a computer scientist. I'm a mathematician, so we try to write it in a way that's accessible. If you're in academia, you're all of us in this room and on Zoom are smart enough to read this book. You won't find it at the airport kiosk, but there's also no really sophisticated math there, so it's kind of in the middle. And so what happens for our cute little example? So this is the optimal solution, 1 over alpha. If we do our bi-level scheme, we do this maximum likelihood procedure, we really get a bad answer. This is way too optimistic. We get a delta to the power 1 over alpha plus 1. It's way too optimistic. And the reason is that in heavy tails, if you have a Pareto, like if I'm telling you I lost 1 million on the stock market, then in the exponential world, I may have lost 1 million, or I may have lost 1 million and 100 euros. But in the Pareto world, if I say I lost at least 1 million, I probably lost 2 or 3 million. Like the overshoot is really big. And so in the maximum likelihood, we do this integral. We replace the integral with the supremum. And in the light-tailed world, that's a good approximation. But in the heavy-tailed world, we cannot throw away the rest of the integral. We need to take into account everything. And so this is why you have to be careful in this form. The level approximation doesn't work. CVAR nicely is exactly equal to the optimal solution times 1 minus 1 over alpha. And that's because of this overshoot and the scaling of the Pareto. Okay, and in the case of the sampling, the problem with that is that the maximum, if you compute the expected value of the maximum, you'll find out that you have to normalize with k to the power 1 over alpha. But then, so in the light-tailed world, this scaled maximum converges to something nicely deterministic. In a heavy-tailed world, it converges to a random limit. But this is bad news. There's no way you're going to have any theoretical guarantee on optimality, because there is no equivalent of law of large numbers like we had in the light-tailed case here. It stays random. And so any kind of optimality results in terms of cost, surely you can limit in all sorts of ways the number of constraints, but there's not going to be any theoretical result here. Like, I would be very surprised that it's going to work. Maybe with some hybrid scheme, I haven't thought about it, but like, I don't know how to do that. It would be cool if somebody does that. So this is the simplest example. How does this example extend? The answer, in the interest of time, it does extend. We again here have this whole dependence modeling in the tail, that I'm not going to bother you with. You have to do this entire scaling like we did for the light-tailed case here. There is another convex program. So we get another convex program emerging in the limit, involving an expected value of phi over random variable theta, which essentially we assume that L divided by its absolute value, condition that this is large, converges to some random variable theta that kind of encodes dependence in the extreme values. And that appears in the limit, and that's a nice convex program. So a nice convex program appears in the limit, that gives you the heavy-tailed analog of theorem 1. And then you can use that to analyze CVAR. So for the one-dimensional case, we had the ratio is exactly equal to 1 over 1 minus alpha, and we see in the more general case it converges to that. So this is the optimality gap for CVAR. And sampling, we could already have refrained saying, okay, it doesn't work, we have this one-dimensional case, but we also show in general for the multidimensional sampling version, if you sample k times, this is the way you have to scale, and then the optimal solution of your linear program converges to a random variable. But to describe where this random variable comes from requires random set theory. If you really want to know the details, come with me on Wednesday. I'm going to the math department at Copenhagen University, where they eat this for breakfast, and I'll explain it. Or they will explain it. Because, yeah, but it's kind of like, so for heavy tails, it's like, so for light tails, I would argue that you can't make any big mistakes. But for the heavy tail case, you have to be more careful. So bilevel could be an alternative here, because CVAR and sampling have more serious drawbacks than they have in the light tail case. Obviously, there are always trade-offs between complexity, feasibility, optimality. There is the disclaimer that I just looked at the vanilla version of these algorithms, and no matter what kind of sophisticated algorithm you're going to come up with, at least the asymptotic analysis we did kind of sets a benchmark on what type of, how the optimal solution of the original problem behaves. And I think, yeah, more sophisticated algorithms, a combination of sampling and a bilevel, like this combination iteratively perhaps, is a good way to go. A big issue is the uncertainty in P and phi that you have to resolve in practical issues. So like Jalal said, you don't know if something is heavy-tailed or light-tailed for sure, because it's an asymptotic property. No matter how much data you have, it's finite. And so this is again also in the power grid situation. This is something we are running into now. So if you go back to FCR, there are multiple products that you can procure, and the question is, what is the best mixture to avoid escaping the frequency out of this region with high probability? And you could argue that you get a CC optimization problem with small delta, but then the problem is that we know the model for a good model for a frequency. If we have the full physical model, it's not so easy. You have this oscillatory terms and so on. You have to model the dependence on Li. So if we, based on our preliminary findings, like the Gaussian noise is fine for FCRN. We're working on a paper, but maybe for FCRD you have to be more careful, based on the frequency data we've seen. And I've also seen that. Yeah, and then like in the Netherlands, we had to determine how high should dikes be to avoid a flood, and the benchmark there was once every 10,000 years. And in the 60s, in 1960, they at the CWI they computed 5 meters and 9 centimeters above a certain level, above some sea level. And that should be it. And then the government thought 4.5 meters, and then they skipped the 9 centimeters, so there was a charismatic statistician that convinced people in The Hague, the government, they should not do 4.5 but 5, and so success story of mathematics. But then 20 years later, there was more sophisticated extreme value theory, more sophisticated ways of extrapolating beyond data. They used the more sophisticated mathematics to redo the entire computation. Turned out that 4.5 was actually not that bad. And so like, and if you do now, so like extrapolating beyond data is always difficult. And now like we have the problem in designing the dikettes in the rivers. Like we have also problems with the rivers because if there is, last week there was a hurricane and like France got a lot of rain, but then there is a river in France and the water comes to the Netherlands and we have problems with our dikes. And then that's also there are more clever ways of making decisions under uncertainty is that like you do the projects with the least uncertainty first. So you have to think, you don't have to spend 100 billion immediately on changing everything. You just look, where is the most gain to be made with the most amount of certainty. And because in practice, we don't have enough technicians to fix our system anyway, and you have to start somewhere, and then mathematicians can help to tell you where to start. So going back to the title, there's really a question. If there's one takeaway as a probabilist, and I trust that engineers will not make the same mistake as economists. You're more careful people. I'm not saying more smarter, at least more careful, but be careful with Gaussian models, I would say. And also, not just that the tail is Gaussian, but also that the dependence, you have to be careful there. And the problem, if you want to use this chance constraint in a rare event regime, the main theoretical challenge is, I think, how can we deal with the robustness against model uncertainty? Like obviously distributional robustness has been suggested already, but the question is also there, like how efficient, there is a fundamental trade-off between efficiency and conservativeness. That I think it would be good to have a framework for that. And I didn't say anything about AI and I just thought of mentioning it. But maybe I should have kept it out of the talk. That's it. Thank you for your attention.
Thanks a lot. I really enjoyed. So people online and also here in person, feel free to, any question, either online or here from the audience.
I'm a bit curious about these EU regulations with the 20-year limits. Is that conditional on some model that they give you, or how are you supposed to know that this will never happen?
Well, there was this call for consultations last year, and people responded to that, and it was very detailed on how the model should look like, what the model should include, so what the time granularity of the model should be. They really specified it in detail. Okay. Yeah, I can find the link and send it to you if you're interested.
Thank you.
Any other question? Let me ask. Yeah, sorry.
What about multimodal distributions? Well, is there any way that we can integrate that into
multimodal distributions? Yes. Like you have like multiple,
multimodal.
Well, in my setting, because I look in the delta smaller region, so then let's say the origin, I normalize everything that the origin is also the expected value. I'm assuming some kind of symmetry here. I'm looking, how does the density look far away from the origin? And so then I just scale away that thing. Yeah. But I think that I assume that it scales like a power law. So somehow implicitly, after taking limits, the multimodality is not.
Makes sense.
People online, if you have any questions, just write in the chat box and I'll give floor to you. But meanwhile, I can ask a couple of questions. So what is this exactly? Be careful with naive models of dependence between assets. Could you please elaborate on if we do this, if we have naive models of dependence, what happens?
Well, I think that was clear, like in at least in the financial world, that people they thought that like risk was diversified, that if one asset fails, the other one doesn't fail, and you have you have these CDOs where you chop up assets in little pieces, you throw little pieces of different assets into one big piece of garbage, as you might call it right now, the CDOs. And then it turns out that those risks were much more dependent on each other than it would be, so then everything failed at the same time. And I mean, they're like, yeah, so they're like, usually there is some hidden structure, like if I, for example, if I say like I was in an airplane and everybody was 2 meters tall, then I was probably, there was a basketball game, and then the basketball team was in the same airplane as me. There's usually one root cause that causes the dependence.
And we discussed a bit about the conclusion of the light tail distribution, but what about the heavy tail? What's the conclusion? All models, they suffer. That's kind of what.
Well, I would say they're like, at least under our assumptions and under the big caveat that the probability method is known, that we know have a good, then the bi-level one
might be better.
Yeah, so our version of the bi-level where we don't do the maximum likelihood, but we use this. I went a little bit quickly there, but like if you use the heavy tail modeling assumption, the multivariate extreme value theory framework,
might be better.
Yeah, is better.
C-bar definitely is super conservative.
Well, yeah, the C-bar is like a factor 1 minus 1 over alpha away, and for the sampling, you just don't get, it doesn't normalize, it doesn't converge. It converts to something random, so it really depends on your sample, and there's no way, I don't see at least how to get rid of that. But it's important to get rid of it, but it requires a more sophisticated way of sampling, I think.
Another question, I thought I will ask the last one. Well, I love it. Good. In your general chance constraint modeling, you just said, okay, we have a function of phi, we have a function of phi as a function of what, the L and X.
Yes.
But you never said where this L stands. Is it in the right-hand side or left-hand side? And you had a very, general, you didn't distinguish where this random variable appears, but does it matter?
Well, that's a good question. So let me go to this formulation.
Or even the first one.
Yeah.
Yeah, here.
Yeah, so
it doesn't matter what phi is, whether L is in the right-hand side or.
no, you can always renormalize it. You can always renormalize it that one is the right-hand side. But yeah, you're often like if you have random linear program, you have like on the right-hand side, you have for example, then you typically have like in linear program, I always write A of X is less than or equal to B, and then A and B can be both random, and then you would have to normalize everything so that there is one at the right-hand side. So you have to normalize the matrix.
But my question is that depends on where L stands, the right hand or left-hand side. Does it impact our choice of the method we like to use?
No.
Yeah.
But with the caveat is that if the L is on the right-hand side and I want to transform it in this form and I divide and I get one over something here, then the 1 over something is light-tailed, the 1 over something is heavy-tailed. You understand what I'm saying?
Yeah.
So then if you divide by things, the left tail becomes the right tail and vice versa, so you have to be a little careful.
Good. Just for your information, Bert will be with us until Thursday noon.
Yes.
So if you wish to meet Bert, please let me know, and we can definitely find the time slot for you to do with Bert. Okay. Thank you so much. Let's thank Bert again. Thanks for joining.
Thanks. Thank you.